And now, as you can see, we'll be starting our flash presentations. So there are some rules. There it is. So judging will be based 50% on the content and quality of the demo and 50% on the communication skills on stage and at the table. The judges will be BPI researchers and staff and our industry experts as well. So I have been ordered to be absolutely draconian with the time limits here, and to that end, I have been given a gong. So once your time limit has reached and you hear the gong, please stop talking immediately, or else our judges will penalize you very harshly. So for our first presenter here, we have Daniel Barker-Rothschild. Time begins when you start.
As a result of accelerating climate change, drought is expected to become increasingly severe and frequent, disproportionately impacting northern latitudes such as Canada. And not only is drought responsible for more annual loss in crop yield than all other pathogens combined, but it can also alter the chemical composition of plants, directly impacting how we process these resources. In this context, today, I want to talk about what we can do to prepare for the impacts of climate change. My work focuses on understanding the effects of drought stress on the chemical composition of Douglas fir and western red cedar wood to better understand its impact on their value as industrial feedstocks. And in this way, not only can we use this information to help better process these resources, but it can also inform selective breeding strategies so that we can actually tailor our forest resources for more efficient processing. And so, all right, thank you.
Thank you, Daniel. For our next speakers, or the rest of our speakers, we'll have you do a quick introduction before we begin our time.
Okay, cool. Can I start? Introduction?
Just your name, yeah.
Yeah, I'm Sahar. I'm a postdoc working with Dr. Tarna Solati at the Department of Wood Science, Faculty of Forestry.
Excellent. When you start speaking, we'll begin.
Oh, is this?
Begin whenever.
Okay, cool. So, slash pile burning is responsible for around 9% of BC's emissions. Now, if we could only stop that practice and produce more bioenergy, biofuels, and byproducts from slash, we could reduce the waste, limit the air pollutions, and create more job opportunities and gain more economic and carbon benefits. Now, we could do that by establishing a distributed network of biohubs close to supply areas where we can produce high-value advanced bioproducts that could then be sold to large centralized biorefineries and biochemicals down the chain. Now, in addition to worrying about the technological advancements and performing techno-economic assessment, it is important to do supply chain optimization to minimize the costs related to logistics activities, which is very huge, and emissions by improving the supply chain network design and also the activities like slash handling, transportation, storage, pre-processing, and that's all. Thank you.
Thank you very much.
Hi everyone, my name is Julia Atzi, and I'm a master's student working under the supervision of Dr. Orlando Rojas in chemical and biological engineering. Colors are found everywhere in nature. Some arise due to pigments, like in fruit, whereas others arise due to the arrangement of highly ordered and periodic structures, like in butterfly wings. Lignin is an abundant biopolymer found in wood, but it has a brown color that limits its applications. So how can we generate more colors from lignin? To do this, we can produce nanoparticles with various sizes and surface chemistries. To achieve nanoparticles of the same size, we can use a centrifugation technique. Centrifugation can also provide external forces that pack these lignin nanoparticles into highly ordered lattice-like structures. These lattice-like structures can produce photonic color across the visible spectrum, with the color corresponding to the lignin particle size and the spacing between these particles. This work can open the door for lignin to be used in broader applications like cosmetics, photonic materials, and sensors. Thank you.
Hello everyone, my name is Chun, a PhD student and a supervisor of Dr. Orlando Rojas. So I'm thinking that everyone in this home would like to be more sustainable and agree that forests is the key for the global sustainability. As part of the waste from the pulp and paper industry, that we gather the bark and try to fabricate some value-added materials out of bark. This drives us to look into the function of the bark, and inspired by indigenous people that use the bark slurries to apply on the skincare products, we made some cosmetics. And another application of the bark materials is we made so-called eco-home materials that can lower the food carbon print and save the energy. Fundas at C5 to go to more details that how we enable all the functions required in the, one building segments. Thank you.
Hello everyone, this is Huimin Zhou here. In this study, the spodumene was introduced into the food waste high solids emphatic hydrolysis and bioethanol fermentation process to enhance the product yields. Under the regulation of spodumene, the substrate released more than 90% of the theoretical reducing sugar, and the glucose concentration increased by 140 grams per liter, and the bioethanol yields increased by 19 and 22%. When spodumene was 1% and 2%. The addition of the spodumene in the food waste high solids emphatic hydrolysis system increased the metabolism of the yeast, and finally 1% was suggested for the practical use. This study deepened the understanding of the spodumene in high solids emphatic bioethanol fermentation system. Thank you.
Introduce yourself first.
Okay. Hello, everyone. My name is Chun. I'm a third-year PhD student. My supervisor is Professor Feng Jiang. Okay. Today, my research is about all-cellulose hydrogel-based wood adhesive. To replace the traditional formatted-based wood adhesives, we fabricate a hydrogel from cellulose, and it is made up of all-cellulose structure. And by utilizing the hydrogen bonds and mechanical interlocking between the adhesive and the substrates, we can use our adhesives for bonding different materials, including wood, plastic, rubber, and even graphite. Here are a simple demonstration here. You can see that I can stand on this wood panel. Sorry. So it's very strong and very potential for replace the traditional formaldehyde-based wood adhesives. Thank you, that's all.
I am Yizhou under the direction of Professor Orlando Rojas. Today I'm going to show the new development at the Bioproduct Institute. Today, virtually all vegan leather available in the market are made from the bio-based material but coated or blended with a petroleum-based material, such as polyurethane or polyvinyl chloride. This combination made the material not only not easy to recycle, but also cause a lot of microplastic pollution to the environment. Here, we propose a strategy to partially remove the lignin from the wood veneer, and also by welding and weaving technology to produce this strong, flexible, and circular bio-based material. The strength development was achieved by welding and weaving, and the supple property was achieved by partially remove some component of the wood material. By using this plant-based protein coating, thank you.
Hello, good morning, everyone. My name is Penghui. I'm a postdoc from Dr. Feng Jiang's group. So can I get a start? Yeah, so here is the plastic bag. So when we mention plastic, what fields first come into mind? Convenience or pollution? Yeah, I think different people have different answers, but there's no design that plastic have caused a severe pollution to our environment. At a research from Wood Science, what can we do to reduce plastic pollution? Yes, we provide our solution. In the lab, we convert correct pulp into a biodegradable and transparent cellulose film through mechanical blending combined with the cold alkali treatment. This process is very simple, but the film we prepare is stronger than most traditional plastic film and also more stretchable than most commercialized packaging bags. So our technology had been reported by over 14 million and patents had been filed. Now we work on scaling up. We think our technology will, thank you.
I really love this gong.
Hi everyone, I'm Zhaodong, a visiting PhD student of Orlando Rojas. Please quickly imagine that you are trapped in a dangerous and lonely island. No people else, no water, no food. But you are lucky enough. Don't hurry, you have a machine like this. This machine is a cellulose foam-based TNG. It can transform my body motion into electrical energy. I'm not sure you can see it. Sorry? Yeah, don't hurry, this is a rescue signal. Yeah, it also can collect water wave, wind, and other low-frequency environmental energies. After the storage and transfer, it can meet the demand of self-power. So, please firmly believe that cellulose-based form has the potential of saving our life. Thank you.
Hi everyone, my name is Chun, a PhD student of Professor Feng Jiang. In our study, we use a microfibrillated cellulose fiber as a raw material to fabricate cellulose-based foam, eliminating the need for chemical treatment of cellulose fiber. The cellulose foam was reinforced by an organic-inorganic network, which are essentially hydrogen bonding and coordination interaction in our case. The foam has a high mechanical property, even capable of supporting the weight of an adult man. It's me on the top left. And our foam is reusable and biodegradable. We believe that our foam will boost the market interest of bio-based product and bio-based economy. Thank you.
My name is Marina Mehling, and I'm a PhD student with Orlando Rojas in Chemical and Biological Engineering.
You go.
Can you stop the timer?
Oh, sorry.
Thanks. 8 million people worldwide suffer from corneal blindness and require a cornea transplant, which replaces the outermost layer of the eye. However, the leading artificial cornea, called the Boston K-Pro, has an 11.1% failure rate. This means that 11 out of every 100 people who receive this device will go completely blind after 5 years. The reason for this high failure rate is the Boston K-Pro uses a plastic that isn't fully biocompatible. It causes blood vessel and scar tissue formation that actually physically blocks a person's vision. To combat this, we're innovating a new artificial cornea with bacteria-synthesized cellulose. Bacteria cellulose is biocompatible, and it offers high tensile strength. These properties enable it to already meet applications in wound repair. However, it's not natively transparent, so our main challenge in this work was innovating a way to enhance its transparency, which we successfully did. We think this material may be the next best artificial cornea. Thank you.
Nice timing.
Good morning. This is Lael. I'm Glen. We're both undergraduate engineers and researching kombucha leather. This is kombucha. It's a drink fermented from black tea using different bacteria and yeast, and it takes about 1 to 2 weeks to produce, and it's very delicious.
And this is kombucha leather. This is a byproduct that forms because of the fermentation process of the kombucha, and it takes around 3 to 4 weeks to have a viable sample.
If I'm producing this, that's a waste byproduct for me because it's way too thin.
If I'm producing this, that's a waste byproduct for me because it becomes too fermented and acidic.
To bridge this gap and eliminate the waste, we're working on different parameters to make the kombucha fermentation process compatible to produce both of these products. We found that by harming the kombucha layer midway through the fermentation, we can produce a layer that's 4 times thicker than it would have been otherwise, thus making a 4-week equivalent leather in the 2 weeks that it takes to ferment this, making it so that we can have a delicious drink and a completely sustainable leather alternative that has a lower carbon footprint. Thank you.
Thank you.
Hello, my name is Isabella, and I'm an undergraduate student in Dr. Rojas's group at BPI. Bacterial cellulose is one of the most abundant biopolymers. In the red wine vinegar industry, for example, over 3 million tons of bacterial cellulose are produced and discarded annually. The purpose of my work is to valorize this waste product, promoting a circular bioeconomy. This bacterial cellulose is unique since it contains tannins. These are the compounds that provide the astringent flavor in red wines. In the lab, I recreate the vinegar process by inoculating red wine over a 14-day fermentation period and harvesting the bacterial cellulose. This bacterial cellulose undergoes a novel dissolution, regeneration, and cross-linking process to produce our films. Thanks to the tannins in the films, they possess unique antioxidant and antimicrobial properties, making them excellent candidates to replace plastic in the food packaging industry. Thank you.
Hello, I'm Yeedo Chun. I'm a PhD student working under Dr. Orlando Rojas. I work in the domain of microfluidics. Microfluidics is the study of the behavior of fluids at sub-millimeter scale. And so what we can exploit at that size scale is the very low Reynolds numbers or very high regularity and predictability of those flows. You can see example in kind of the left-hand side middle bottom there is the generation of bubbles in such a microfluidic system that enables you to produce these bubbles of monodispersed size. We can exploit this by collecting them and solidifying them with polysaccharide solutions, and we can form a range of polysaccharide foams with monodispersed pore size as well that have a myriad of interesting and high-end applications. My main innovation here, however, is replacing the very expensive market chips that cost around $500 with this simple device that costs a total of $5 to make, and you can order all of these components from McMaster-Carr and get them in 2 days. And so I hope with this kind of development of the technology that will enable more research and innovation with our colleagues in the future. Thank you.
Hello, everyone. My name is Pu Yang. I'm a PhD student under the supervision of Dr. Xiaotaobi and Dr. Feng Zhang. Nowadays, there's a certain demand for bio-based carbon materials with large surface area for sustainable energy storage. Current methods rely on high-temperature biomass activation, raising concerns about low carbon yield and high energy cost. To address this challenge, we focus on fine-tuning and enhancing porosity at low temperatures. Our innovation centers around an adaptable and recyclable molten salt system for carbonization of chitin from crustaceous waste at a mere 500 degrees C. Upon melting, the salt ions undergo fast diffusion towards active sites, creating and retaining numerous pores whose sizes are modeled by the salt cations. So the yielded biocarbon shows ultra-high surface area, tunable pore size, and various heteroatoms, yielding outstanding supercapacitor performance. Beyond advancing the scientific understanding of pore structure engineering, our work holds promise for diverse applications such as CO2 capture, water treatment, and catalysis, making contributions to broader societal issues. Thank you.
So hello, everyone. My name is Yizhou. I'm a postdoc in Orlando Rojas group. So we extract chitin from crab shells and then further deconstruct them into nanoscale. We call them the nanochitin. The suspension of nanochitin can actually become a nanochitin hydrogel within a basic vapor bath. By controlling the hydrogelation process, we can create very interesting patterns that has periodical layers. For example, we do the in situ biomineralization by co-precipitating with the calcium apatite. As such, you can get this layer by layer structures that has very interesting optical performance. Also, we can use the magnetic manipulation where we use the hydrogel framework to fix the iron decorated nanochitin. And we can actually create those barcode-like structures that encrypt certain message, like the pattern of UPC in our hydrogel. Thank you.
That's good timing.
Hello, everyone. I'm Zhangmin from Dr. Orlando Rojas group. Today, I will present the dislocation mechanism of the alpha-chitin crystal. Alpha-chitin crystal exists in the sea creatures' shears, which are wrapped by the chitin-binding proteins and biominerals. The theoretical result demonstrate the covalent bond of the chitin is around 5 or 7 gigapascal, which is much higher than the tensile limit of the chitin-based Vulcan materials. Our atomic simulation demonstrates the shear stress is in the same magnitude of the chitin-based materials, tensile stress. So we hypothesize that shear deformation is the dominant source determining the tensile limit of the chitin-based materials. Also, we analyzed the non-covalent interaction between the chitin layers, and we found London dispersion interaction is the dominant role to determine the cohesion of the chitin-based materials. Also, the adaptability of the London dispersion is stronger than the hydrogen bond, which ensure the recoverability to withstand the continuous shear in the complicated environment of the chitin-based materials. Thank you.
Hello everyone, I'm Akash. I'm a PhD student under Johann Foster's group. So everyone is talking about climate change, but why is it changing? Well, one of the main reasons is the greenhouse gas emissions coming from industries, especially metal and plastic industry. Now, we can't stop these industries, but there's a way we can replace some of these materials with wood. Yes, you heard me right, I'm saying wood. So in my research, I try to modify the wood in such a way by giving some physical and chemical treatment by making it strong as steel or making it cushion for packaging application. Now I'm gonna go crazy. We can also give magnetic properties to the wood. The best time to plant a tree was 20 years back, and the second best time is now. So will you join me to fight climate change by planting a tree at a time? Thank you.
All right, big thank you to all our presenters. I'm going to ask one more round of applause for everybody that got up today. It was really excellent. And now